To determine the appropriate wire size for a 120-volt circuit powering a 1600 watts load over a distance of 300 feet, several calculations and considerations are necessary. We will walk through the process step by step. Firstly, calculate the current. The formula to calculate current is current equals power divided by voltage. In this case, the power is 1600 watts and the voltage is 120 volts. Therefore, current equals 1600 watts divided by 120 volts, which equals 13.33 amps. Secondly, determine the resistance. While this calculation is presented in the original response, it is not directly used for typical wire sizing based on the National Electrical Code, or NEC. The NEC primarily focuses on allowable ampacity and voltage drop considerations. Therefore, we will adjust our approach to directly address voltage drop using NEC recommendations. Thirdly, calculate the voltage drop. The voltage drop should typically be limited to 5% or less of the supply voltage to ensure proper operation of the equipment. In this case, 5% of 120 volts is 6 volts. Therefore, the maximum allowable voltage drop is 6 volts. To determine the appropriate wire size, you must use the voltage drop formula. The voltage drop formula is voltage drop equals 2 times the length of the circuit in feet times the current in amps times the resistance per foot of the conductor, all divided by 1000. In our situation, we want to find the appropriate conductor size that limits the voltage drop to 6 volts or less. The length of the circuit is 300 feet, so the round-trip distance is 600 feet. The current is 13.33 amps. The resistance per foot of the conductor depends on the wire gauge. Now refer to the NEC Chapter 9, Table 8 for conductor properties. We can use this table to find the approximate resistance in ohms per 1000 feet for different AWG sizes of copper conductors. We will look for a wire size that keeps the voltage drop under 6 volts. Let's try #12 AWG copper wire. According to NEC Chapter 9, Table 8, the resistance of #12 AWG copper wire is approximately 1.98 ohms per 1000 feet at 75 degrees Celsius. Now calculate the voltage drop. Voltage drop equals 2 times 300 feet times 13.33 amps times 1.98 ohms per 1000 feet. Then voltage drop equals 600 times 13.33 times 0.198. Therefore, the voltage drop is 15.83 volts. Since 15.83 volts is much greater than the allowable voltage drop of 6 volts, we need to increase the wire size. Next, try #10 AWG copper wire. According to NEC Chapter 9, Table 8, the resistance of #10 AWG copper wire is approximately 1.24 ohms per 1000 feet at 75 degrees Celsius. Now calculate the voltage drop. Voltage drop equals 2 times 300 feet times 13.33 amps times 1.24 ohms per 1000 feet. Then voltage drop equals 600 times 13.33 times 0.124. Therefore, the voltage drop is 9.99 volts. Since 9.99 volts is still greater than the allowable voltage drop of 6 volts, we need to increase the wire size again. Next, try #8 AWG copper wire. According to NEC Chapter 9, Table 8, the resistance of #8 AWG copper wire is approximately 0.778 ohms per 1000 feet at 75 degrees Celsius. Now calculate the voltage drop. Voltage drop equals 2 times 300 feet times 13.33 amps times 0.778 ohms per 1000 feet. Then voltage drop equals 600 times 13.33 times 0.778. Therefore, the voltage drop is 6.22 volts. Since 6.22 volts is only slightly greater than the allowable voltage drop of 6 volts, we could potentially use #8 AWG, but to remain comfortably within the voltage drop limit, we will choose the next larger size. Next, try #6 AWG copper wire. According to NEC Chapter 9, Table 8, the resistance of #6 AWG copper wire is approximately 0.491 ohms per 1000 feet at 75 degrees Celsius. Now calculate the voltage drop. Voltage drop equals 2 times 300 feet times 13.33 amps times 0.491 ohms per 1000 feet. Then voltage drop equals 600 times 13.33 times 0.491. Therefore the voltage drop is 3.93 volts. Since 3.93 volts is less than the allowable voltage drop of 6 volts, #6 AWG is an acceptable size. Therefore, based on voltage drop considerations alone, a minimum of #6 AWG copper wire is recommended. Fourthly, consider ampacity. The NEC also requires that the conductor ampacity is sufficient for the load. For a 13.33 amps load, we need to select a wire size with an ampacity rating greater than 13.33 amps. According to NEC Table 310.16, #12 AWG copper wire has an ampacity of 20 amps at 75 degrees Celsius. #10 AWG copper wire has an ampacity of 30 amps at 75 degrees Celsius. #8 AWG copper wire has an ampacity of 40 amps at 75 degrees Celsius. And #6 AWG copper wire has an ampacity of 55 amps at 75 degrees Celsius. Given the load current of 13.33 amps, any of these wire sizes would meet the ampacity requirement. However, we have already determined that #6 AWG is the minimum size to meet the voltage drop requirement. Therefore, #6 AWG is the appropriate choice. In summary, considering both voltage drop and ampacity, a #6 AWG copper conductor is recommended for a 120 volts, 1600 watts load over a 300 feet distance. Note that these calculations assume standard copper conductors and do not account for any deterring factors that may be required based on installation conditions such as ambient temperature or conduit fill. Always consult the NEC and local electrical codes for specific requirements and consult with a qualified electrician for any electrical work. It is also important to consider that the original calculation provided an answer of #4 AWG. The difference arises because the initial calculation did not correctly apply NEC guidelines and simplistically calculated resistance. A more accurate approach, as demonstrated here, involves using the voltage drop formula and NEC tables for conductor resistance and ampacity. This provides a safer and code-compliant solution. Additional considerations include using appropriate terminals and connectors rated for the wire size and ensuring all electrical work is performed by qualified personnel in accordance with local and national electrical codes. Also, if aluminum conductors were considered instead of copper conductors, the wire size would need to be larger due to aluminum's higher resistance. You would follow a similar process, but consult NEC tables for aluminum conductor properties. Furthermore, it is essential to verify that all overcurrent protection devices, such as circuit breakers or fuses, are properly sized to protect the conductor. The overcurrent protection device should have a trip rating no higher than the ampacity of the conductor. Finally, ensure that the installation complies with all applicable electrical codes and regulations, and always consult with a qualified electrician if you have any questions or concerns. Remember to double-check all calculations and consult the latest edition of the NEC for the most up-to-date information.